So my name is Peter. I'm since about a year. I'm in Munich Technical University, and I was postdoc here from 2007 to 2010. So it's already my second reunion, and it's a pleasure to introduce Amichay Vardi. He is, I think, a frequent visitor here, and as you see here, also currently visitor at ITAMP, and I'm looking forward to it.
Thank you. First,
you need the mic.
Oh, the mic.
Yeah.
This one. Is this on? No, okay. Probably not, right?
The button is on top.
On top?
Yeah, this little one, just move it.
Mm-hmm. Okay. Do they hear me now?
Yeah,
is it? Yeah, it's working? Oh. Fair enough. Okay, so first I'd like to thank Hossein again for organizing this, Joe and everybody else, for organizing this wonderful gathering. And it's great to see everybody, Kate over here and everybody. It's rather amazing to see both the breadth and the depth of the talks over here. So it's a great event, and thank you. I thought that it would be nice if I'll tell you about two recent projects that use as building blocks stuff that, oh, is there a, yeah. Yeah, for some reason. Yeah, stuff that we've been working on over 20 years ago as here at ITAMP. And in fact, James Anglin is also a co-author on one of these new projects, of those two recent projects. And so it's another example of the incredible longevity of ITAMP collaboration that was already demonstrated in all the previous talks. So I thought it'd be a nice tribute. So, few fun facts on the Bose-Josephson Junction, which you probably also know. It's also known as the Bose-Hubbard dimer or the Lipkin-Meshkov-Glick model from nuclear physics. It's the simplest bosonic model in existence. It involves only two second quantized mode, plus and minus with local interactions. You use Jordan-Schwinger, and you scale time per the hopping probability, and the system maps to a spin problem. To a spin problem with a single dimensionless interaction parameter. Now, in the classical limit, it has three dynamical regimes. There's the Rabi regime, where the dynamics is dominated by linear oscillations at the Josephson frequency. There's the Josephson regime, where there's coexistence of a linear C and two nonlinear islands that are separated by a separatrix. It's essentially a pendulum. And there's the Fock regime, where the linear area becomes too small to support even a single quantum state, and the ground state itself becomes the Fock state. That's a primitive version of the Motte-insulator transition. Now, the quantum mechanical spectrum of the Bose-Josephson junction of the dimer is reproduced to excellent accuracy by semi-classical quantization. That is, if we require the action, the area enclosed by a single classical trajectory, to be a multiple integer of the Planck cell area 4 pi over n, this gives us the spectrum to great accuracy. In the Rabi regime, which will be the subject of this talk, we will focus throughout this talk, it would be in the Rabi regime, we could in fact have an analytical expression for this area in terms of complete elliptic integrals of the first, second, and third kind. And so given the number of particles, the energy of the dimer, and the interaction parameter, we could know the number of Josephson excitations for the lack of another term, we will call from now on Josons. So one of the very early speculations concerning the bosonic Josephson junction was the possibility to observe collective many-body tunneling and macroscopic cat state. If we look at the island-supported doublets, we see that there are, in fact, odd and even superpositions of all particles on one mode or the other. The obvious problem and the known problem is that the scaling of the gap between these two is awful. It scales exponentially, it becomes exponentially small with the number of particles, so any tiny perturbation would kill the cat and drop the system to one side or the other, to one mode or the other. So this makes it practically impossible to observe. Now, the first story I'd like to tell you today is how using two of these bosonic Josephson junctions, two Bose-Hubbard dimers, we could enable, in fact, the observation of collective many-body tunneling. And the idea is to use chaos. In, chaos-assisted tunneling, there are two integrable islands, and the tunneling between them fluctuates. The tunneling gap between them fluctuates erratically over many orders of magnitude as a function of external parameters or as a function of the Planck constant. The underlying mechanism is simple. It is just a mixture of the system symmetry and chaotic level repulsion. Consider a doublet over here, and that is approached from below by a state that is supported by the chaotic C. And the upper doublet state, which belongs to the same symmetry class, is repelled by it, whereas the other one is from a different symmetry class and therefore is completely unaffected. As a result, the tunneling gap, the doublet tunneling gap, is enhanced by many orders of magnitude, and this is the source of these fluctuations. The same fluctuations as in universal conductivity fluctuations and so on. Now, depending on which state gets affected, here's an example where the lower one is getting repelled. The tunneling gap could be enhanced, it could be suppressed, or could even be completely canceled at a given value of the external parameter. And the idea now is to use this mechanism in the case where the cat state, the doublet, is a doublet of macroscopic cat state. That's the idea. Okay. So this is our system, two coupled bosonic Josephson junctions. There's weak coupling between the modes and strong coupling inside each of the dimers. Classical limit is obtained as usual by replacing the operators by C numbers, and the system has two dimensionless parameter, the dimensionless hopping and the dimensionless interaction. Now, in the adiabatic limit, we have an adiabatic invariant, which is the sum of the actions of the two dimers. So this is an adiabatic invariant that enables us, via a series of a long chain of Holstein, Primakov, and Bogolyubov transformation, to eliminate the fast internal degrees of freedom and be left with dynamics that corresponds to the slow exchange of particles and Josons, Josephson excitations, between the two subsystems. The effective parameters for Joson hopping and attraction are given over here. So we have the total particle number is exactly conserved. The Joson number is an adiabatic invariant, and therefore we essentially have 2 degrees of freedom, the particle imbalance and the Joson imbalance, and the respective phases that serve as conjugate momenta. So we have this 2-dimensional effective motion. And to quantify chaos in this system, we use the usual criteria of level spacing statistics, many different measures, but basically we look at the statistics of the spacing and see the typical transition. When omega is small, we basically have 2 integrable dimers, and we get Poisson statistics. In intermediate coupling, we get chaos, and when the coupling becomes too strong, we go back to Cauchy statistics, because now we have linear dynamics that the hopping dominates, and we have essentially linear dynamics. Now, the degree of chaos can be quantified by the adjacent spacing correlation function, which is shown here throughout the parameter space. And we see that chaos prevails where the coupling is weak and both dimers are in their respective Rabi regime, which is why we'll keep focusing on this regime throughout this talk. OK, so let's begin with the spectrum of two isolated dimers. So the little omega is 0, and in that case, of course, the good quantum numbers are the total particle number, the total Joson number, the particle imbalance, and the Joson imbalance. All of them are good quantum numbers. There are two separate subsystems. And now we could plot for a given n the states according to the big J, little j, and little n, the total Joson number and the two imbalances. And we color each of these eigenstates according to its participation number in the exact eigenbasis for finite coupling in the chaotic regime. So we see that there is a regime there's a regime where the unperturbed eigenstate mix many exact eigenstates, and in the peripheral regime, they mix only a few. Now, if we take one of these layers, let's take the j equals 10 layer, or j equals 11 layer, and plot the energy of the states as for all the states in that layer, we see that the states that have high number variance are higher in energy because particles repel in one another. The states that have high Joson invariance have lower energy because there is an effective attraction between the interactions. And so the expected dynamics, the expected classical dynamics, would be just a 2D motion in the presence of a central saddle point. If we now take the same j equals 11 surface and plot the classical trajectories, we actually see that the region where we had high participation corresponds to a chaotic region, whereas the region where we had two pairs of regions, where we had low participation corresponds to integrable islands that describe the self-trapping of particles or the self-trapping of excitation, self-trapping of either particles or energy. Now, the exact eigenstates, now you directly diagonalize the system, and the exact eigenstates of the systems must belong to one of four irreducible representation of the system's symmetry group, which is the dihedral group D2. Therefore, the expectation value of n and j must be 0. If we have a cat state, the expectation value of the number difference is going to be 0. But we could arrange the eigenstates according to the variance of the Joson and particle imbalance. And again, now we color them according to their participation in the unperturbed basis. So this is the opposite of what we just saw. And again, now we said that J is an adiabatic invariant, and this is the reason why the spectrum is layered so nicely in layers of fixed J. So if we take again the J equals 11 layer and plot all the points in it, we see different types of states. The states over here, which have high number variance and high Joson variance, are in fact macroscopic cat states where all particles, superpositions of all particles on one subsystem or in the other. The states with low number variance and high Joson variance are again macroscopic cat states, but they are energy cat state. All the energy is in here, all the energy is there. And the states in between with the high participation, as expected, they are the chaos-supported eigenstates. And so the scenario for chaos-assisted tunneling is now clear. We have these cat states. We want to see the gap between them enhanced by the interaction with the chaos-supported eigenstates. And so consider this example. We have this doublet of a B1, B2 states. And as you can see over here, they are just a particle cat states. And it is approached from below by this state over here. The state over here that has a Shannon entropy which approaches the expectation of a Gaussian orthogonal ensemble, which indicates it is chaotic, as also can be seen from its projections on the unperturbed eigenstate. This one comes from below. The B1 eigenstate sees it and they repel. The B2 state, as are all the other states that belong to different symmetry groups, is completely oblivious to it. And as a result, the gap between the doublet states is enhanced over many orders of magnitude. Now, this is one case. Now we have to look at the entire spectrum. So this is a summary of all the gap spacings for two different coupling strengths. And the black points are for 18 particles, and the red points are for 28 particles. And you could immediately see that the usual exponential decay of the tunneling splitting as you get away from the chaos border. The analysis of this data is kind of intricate because you have to make sure that you look at the same points, the same location with respect to the chaos border every time. But once you do it, you get to the following conclusion. When the omega is weak outside the chaotic regime, you get the same exponential decay, rather smooth exponential decay of the tunneling rate with the number of particles, which is the effective Planck constant for this system. On the other hand, in the chaotic regime, we see these huge fluctuations, and note the scale over here. It's 40 orders of magnitude. Yeah, so these are 10 orders of magnitude fluctuations in the hopping rates. And moreover, if we look at the statistics of these splittings, they follow the expected Cauchy statistics, which is the hallmark of chaos-assisted tunneling. So this was story number one. The second story involves another very funny property, very interesting property of the Rabi regime, Bose-Josephson junction, and this is its negative specific heat. We have this closed form expression that I showed you in one of the first slides for the action coordinates as a function of the energy, the particle number, and the interaction parameter. And from it, we could derive microcanonically the usual thermodynamic quantities, such as the entropy, the temperature, and the heat capacity. Now, looking at the entropy as a function of the energy, we first see that the temperature is positive. This is trivial because the density of states increases monotonically for a Rabi regime dimer. If we don't go to the Josephson regime, then the density of states just will increase monotonically, and we'll get the positive temperature. But what's more interesting is that the entropy as a function of energy is convex. And this means, the second derivative, this means that we have negative specific heat. And the implications of negative specific heat are dramatic when you consider two such systems that are brought together in thermal contact. That is, they're allowed to exchange energy while keeping the total energy fixed. And if we look at the entropy change of the system, the total energy change, as a function of the heat transfer, due to the heat transfer up to second order, we see that second law of thermodynamics tells us that indeed the heat needs to be transferred, energy needs to be transferred from the hot system to the cold system. There's no way around it. If delta E is greater than 0, then T1 is smaller than T2. However, the second term tells us that, the negative specific heat tells us, that as energy is transferred from the hot to the cold only gets colder and the hot only gets hotter. And so the temperature difference between the two subsystems grows, so the more energy needs to be transferred at an ever-increasing rate. The conclusion from this is that aggregates of such systems with microcanonical negative specific heat would tend to concentrate heat spontaneously rather than disperse it evenly between all the subsystems. And the most famous examples of negative specific heat are in isolated systems that are dominated by gravity, which are the subject of this area of the university, of course. We know that stars are formed from hotspots in cold cosmic clouds. We know that planets form by accretion in protoplanetary disks. And we know that black holes in asymptotically flat space-time lose energy as they heat up. That's the, or heat up as they lose energy. That's the usual way it's proposed. Okay, so to look at the same kind of phenomenon in our dimer system, let's construct a two-dimensional array of Bose-Hubbard dimer. Again, weak interdimer coupling, strong intradimer coupling. Unfortunately, this is beyond quantum treatment. We did something in a canonical configuration, not a grand canonical, that sort of tells us that we are okay, but everything I'm going to show you from now on is going to be mean field. So we have the mean field equations. And there's one thing that we should note, okay, that it's important to understand, because while the microcanonical specific heat of each dimer subsystem is negative, they're allowed to exchange particles and energy with the environment. This means that the overall description of the system is grand canonical. It's not microcanonical. So the overall heat capacity must be positive. There's the virial theorem and the straight ahead proof that you cannot get negative specific heat grand canonically. However, the fact that each of the subsystems has microcanonical specific heat has a very significant implication on the grand canonical distribution. Because the fact that each subsystem has negative specific heat means that the number of states in the bath, the density of states of the bath would be enormously high as the energy of the subsystem increases. And this means that if we look at the grand canonical distribution, it will have a second peak. It would be bimodal. It would not be the usual just decay. It would have a bimodal form. That would be the grand canonical distribution. Okay, so does the dynamics, mean field dynamics of our system reflect this Fearing instability? You betcha. Here's an example of the particle distribution and the energy distribution, launching the system for a rather uniform state. So we begin with a state with just a bit of noise in the particles in the energy. And the system, and we distinguish between very weak, you'll see immediately why, between very weak interaction and slightly strong interaction still in the Rabi regime. Both cases, the system concentrates energy spontaneously. We see that the energy clumps together, but there's a difference between the very weak and the intermediate interaction strength, because for very weak interactions, the J over here is sufficiently strong to provide some surface tension. And what we get are essentially heat droplets that behave very much like a liquid. If I, let's see if I, it was actually playing. Oops, wrong direction. I'll do it like this to be faster. So if we look, you see droplets are formed and they move around and they wiggle and collide and they are very much behaving like a liquid of heat. Now, for stronger interactions, this becomes negligible with respect to the on-site interaction, and what we get are breathers that are pinned down in one place. But both cases reflect concentration of heat, which is the effect of negative specific heat of the individual system. Now, to what extent does what I just showed you reflect grand canonical statistical mechanics? So here's a comparison of both. These are the two simulations that I just showed you. And we plot the distribution of the number of particles in the dimers and the energy of the dimers. And they are compared over, this is what we actually observe. We just count how many dimers we have with a given n and a given energy. And the shadow over here is the grand canonical distribution that enforces the conservation of the total energy and the total particle number. And you could see this is not great. Yeah, I mean, the agreement is not really good. And in fact, I just told you that the grand canonical distribution should be bimodal. Here it's not, right? I mean, it's just the lower energy. There's no second high energy peak. Why is this? The reason is that the dimer spectrum is bound from above. If it's bound from above and the negative specific heat, if the specific heat is negative, then there is a minimum temperature you could get to. And the temperature prescribed by this conservation law is already below this temperature, so no single system could be colder than the temperature of the collective bath. This is why you get just a single mode. But we do see bimodality. So while negative specific heat alone is insufficient to predict the signature of the Fearing instability, we actually see it. How come? The answer lies in that adiabatic invariance of the total Josephson number, because this ensemble does not account for it. So we now have to, So if instead of just taking the grand canonical distribution, we'll form a generalized Gibbs ensemble that accounts for this added constraint. It's not a separate Lagrange multiplier, because it's completely set by the total number of particles and by the number of particles and energy. However, it is another constraint of the system that limits the motion in the phase space. And so now, if we add this to our ensemble, and construct this generalized Gibbs ensemble, we see a bimodal distribution, and that matches quite nicely with what we actually see. And in fact, you could say that the adiabatic invariance of the Josephson number is really enhances, it amplifies the effect of the negative specific heat, because it adds again this U-shaped M onto the grand canonical distribution. Last slide. Okay, so far we stuck with conserved excitation number, fixed number of Josephsons. The interaction was weak. What if we now try to push this limit and break the adiabaticity? Now, if you do Bogoliubov analysis of all the Josephson modes, it turns out that adiabaticity would break down at 1 minus 4j. This means that there is still room to break adiabaticity while still keeping u smaller than 1, still being in the Rabi regime. And so if we just work, so it's 0.045, that's the coupling, so 0.8 is the critical one. What if we now carry a simulation at u equals 0.84, just above the breakdown of adiabaticity? What we see is a really fascinating behavior, because the system now takes 2 stages. It thermalizes in 2 stages. And okay, everybody knows about prethermalization, but why? I'll tell you in a second why it's so staggering. So in the first stage, the system conserves the number of particles, and we obtain the same breather array that we saw before, the same prediction of the generalized Gibbs ensemble. That's what you have over here. That's at this time, which is the end of the first stage of thermalization. But then it goes on to explore, because we don't conserve the number of particles the number of Josephsons explicitly, it goes on to explore the rest of the phase space and relaxes to the grand canonical distribution. See the matching. So it's a huge prethermalization effect. It's very dramatic. You see this breather array that then disappears. just due to one constant of motion. This is a huge system. Think of the dimensions of this system. It's a huge system. You add one constant of motion. It's way away from integrability. It's not the usual example of a system that's almost integrable. It's just one. It's not even a constant of motion. It's an adiabatic invariant. Okay? And this is enough to generate this very impressive prethermalization effect. Okay, let's conclude. I hope I convinced you that coupling integrable dimers give interesting non-integrable physics even in the weak coupling regime. We could use chaos for the observation of collective many-body tunneling and the stabilization of macroscopic cat states. The adiabatic invariance of the excitation number results in highly non-canonical thermalization to a generalized Gibson sample. And even one adiabatic invariant is sufficient to generate a strong prethermalization effect very far from integrability. Thank you very much.
Okay, thanks a lot for a very nice talk. We have time for a few questions. Yeah.
One question for the first and then one for the second part. So for the first part, if I understood this correctly, so you have this cat state in principle which you would like to see, or you have stuff left and stuff like right, and if you bring in the chaos or let's say the disorder, then these states are not eigenstates anymore of the Hamiltonian, which were before eigenstates being left and being
one
right.
Of them is not. One mixes with the chaotic state, the other is not.
Great. So my question is it rather, can I also view it as a diffusion through this disordered system to reach the other side?
There were explanations of chaos-assisted tunneling along this way. You know, one island couples to the chaotic sea, then the density percolates throughout and gets to the other one.
Exactly.
The problem with this description is it's much slower than what you actually see. That was the initial thinking about these. That was exactly, but it would take much too long to actually does not fit this huge enhancement of the tunneling.
So is this related to this discussion which people had on photosynthesis, like to get from the actually center where the photons reach the photosynthesis chain of like these eight islands to get on the other side, and there was also like a timescale mismatch, or there's a timescale mismatch which is not explained.
Could be. I don't know enough.
Okay.
About it.
Second question was, what sets the timescale of the end of prethermalization?
It depends, of course, on what is the coupling frequency. Yeah, but if you look at the prethermalization, you see that overall we count times in hopping units. So whatever the system and whatever the hopping units are. But you see that the first stage would be about 10, 15 slow oscillations, and the final thermalization is attained at about 1,000 or 10 to the fourth. You're asking about what is the thermalization, the long.
What really sets this prefactor, which is that dimensionless number? So why 10 to the 3? 10 to the 4?
For the actual, I guess it has to do with the rate at which the system, once we gave up the conservation of the total number of particles, it has to do with the rate at which the system explores the classical phase space. That's essentially what you see. So, and this would probably correspond to some largest Lyapunov or something like that. That would be my bet just offhand,
Maybe a very quick question, also the first part. Is there a simple measurement you can do in terms of, let's say, local numbers or something?
There is one that I hid one slide, actually. So I'll just go out. There is a telltale measurement that you could do. just unhide it. It's this one. Now, is this the hide?
Yeah, I mean, we can see it, I think. It's,
oh, you can?
Yeah,
okay, that's good enough. Okay, so basically, the telltale sign of a chaos-assisted tunneling is the existence of two frequencies, because at the resonance, you have both this frequency and this frequency play a part. And so if you look at the oscillations on this side or on that side, they would just be involve a single frequency. In the middle, you get two characteristic frequencies. And this is the ideal case if you just prepare that particular resonance. And this is a more general case where we just took all particles in one side. So it's something that's easy to prepare in the lab. And in that case, you still see in the Fourier transform, in the power spectrum, the same two frequencies. So this is the telltale sign of chaos-assisted tunneling.
Okay, thanks. So in the interest of time, let's thank Ami again. And